Okay, so I will start. Okay, so let's start the last session on statistical learning theory. I think I have received all of your homeworks, so they should be all in. Tam has finished correcting the first homework, so you should receive the grades today, later today. So let's just go back a bit to what we've been discussing last time. So since I know this is not the easiest lecture in the whole course, I will repeat a bit what we've seen last time and then follow on with the Vapnik-Chervonenkis theory. So remember that the building block, the most important block that we have been using so far is called Hustings Inequality. So when we have an empirical average and compare it to the real average, the true average, the probability that this deviation here is bigger than epsilon. And here when I'm saying probability, it's in terms of probabilities on the sample of size n. So I have n points that you're giving me to compute the empirical average. There is a true average somewhere. Given the randomness of that sample of size n, well, the probability that the error is bigger than epsilon, sorry, the difference between the true empirical, the empirical average and the true average is bigger than epsilon, decreases in this way. So here I should have removed B and A because A and B are just bounds on the values taken by F. So basically this decreases very fast, especially in terms of n, the number of samples that you get. If you rephrase this in a more intuitive way by just taking the inverse of this point, the function of epsilon, well, you get that with probability at least 1 minus delta, so if you write delta for this, with probability at least 1 minus delta, well, the difference between the empirical and the true means are controlled by this term. And this term basically decreases with the square root of 1 over n. Okay? So this is a fundamental property that we will use, we have been using throughout the lectures. So here is a drawing that I made the other day. I tried to make it a bit more clean here, which I hope will also help you capture what is going on. So we have a real curve here, which is the true risk. And if everything was given to us, if we had all the information that we wanted, then we would be looking for the minimum of the true risk in the set of all functions from Rd to y. Okay? And that would be f of b here. This is the lowest risk of all possible risks. Since we are using computers and usually we restrict our hypothesis space to a few functions represented by this set G here, well, if we still had access to the real risk, we would be looking for this function here. And the difference between the risk of this function and this risk here is called the approximation error. And you can understand that this approximation error only depends basically on your choice for the function class G. Okay? Now, we never have access to this blue curve. The only thing we can see is the red curve. The red curve is the empirical risk. Here I have put in a line here that's basically at 0 to insist that if you look at actually all possible functions from Rd to y, there are many functions that have 0 empirical risk. But those are not good functions. Usually they're overfitting. And if you look at what I mean by overfitting intuitively is the fact that here the empirical error is 0, but the true risk or the true error would be much bigger. Or here, in this case, it's even the gap is even wider. Okay, so this function actually I should have written here that it's upper bounded by 1. Okay, so it's between 0 and 1. And this is, when there is a big gap like this, this is what we call usually overfitting. Since we are using this red curve, what we try to do is minimize the empirical risk on the function class G. Okay? And the difference between that we get between this Gn here and this G star here is called the estimation risk. Okay? There is a third error that I haven't mentioned, but which is very important in practice, especially when you have a very large data set, and it's called the optimization error. So far I've been talking about approximation error. Approximation error is basically the gap between considering this function and the true risk minimizer. The second one is the estimation error. How bad am I choosing a GN here using a red curve compared to the the best possible G here in this function class that I could have chosen, okay? So I've been talking about those two. There's a 3-1 that I would like to introduce. I'm not going to discuss it further, but it's very relevant. When this red curve here is an empirical average over, I don't know, maybe 10 million points, okay? Usually it can be very computationally demanding to really find the GN, the optimum, okay? So sometimes what we do is we settle for an approximation of that optimum, okay? In some algorithms, typically machine learning, you will not let the optimization error decrease to 10 to the power minus 15. So some people in optimization find it really important to decrease, to find the best minimum up to a numerical margin of 10 to the power minus 15. In machine learning, we never do that. Usually we just stop when we're happy that this is small enough and that the progress has been carried out enough. So in practice, we will rarely really use this GN, the minimum of the empirical risk. What we will use instead is some kind of G tilde n, or I don't know, H of n, which is just an approximation of the minimum. And the gap between this approximation and GN is called the optimization error. So sometimes, if the gap between this and this and this and this is huge, then it's not a problem to have a small optimization error. It's not a big deal. So in that case, this is where people will be looking for heuristics. If, on the other hand, the approximation error is small and the estimation error is small, then it becomes important to also keep the optimization error small. Okay? So I didn't put this in my slides, but I just wanted to tell you about this third source of error. So in the bounds that we have been studying, we have been discussing mostly about this bound here, and we've also discussed a bit about this bound, I think. Let me just recall you what we've been doing last time. Last time when we left, we mentioned Hustings bound for finite families, and then we were about to talk about Hustings bound for countable families. And today we're going to talk about Hustings bound for arbitrary families of functions. And then we will follow with some considerations on VC dimension. SVM will probably for next time, but if we have time, we will start talking about SVMs. So remember what is the problem of Hustings bound? Hustings bound is that Hustings bound for a given function here, if I just fix a function here, and I start drawing randomly samples, it just tells me that the empirical error, the gap between the empirical error and the true error here, this gap here, will be quite small, especially if n increases. Okay? So for a fixed function that I take here, I have red curves which are random, which move around. If you remember, this was the idea of this slide here. No, it was not a slide. It was a script. Maybe I still have it somewhere. No, I've been working on my MATLAB. Sorry. So let me just go back to this. Yeah. So if you remember, I don't know if you've run this script, but it might help you understand better. The red curves, the empirical errors, those curves are random. Those are really random curves on the space of all functions. And what we're just saying is that for one particular function, for this one for instance, the gap between here and here, or here and here, is quite small depending on, you can bound it in terms of n. Okay? So let me just go back now to the picture. However, we cannot use directly Hustings bound on the minimum of one sample to say that this gap here is small. Because this is a contradiction. Hustings bound works when you have set the function before, and then you see samples arriving randomly. Here, what we're doing is we have one sample. It's been costly to gather it, to get it. We optimize GN, but then we cannot have it twice, and we cannot use Hustings bound on that particular sample to bound this. So what people do instead is that they consider uniform bounds. And uniform bounds are bounds which say that for any function in G, in the whole of G, I will try to bound the difference between the blue curve and the red curve. So basically those differences are just those, the length of those segments here between those two curves that cross each other. You have one fixed curve, the blue curve. You have red curves which arrive randomly. And if you can bound uniformly, that is for any function here, say that the supremum is smaller than some quantity, then after that, I can use that uniform bound on one particular instance, which will be the best possible gen in that function class for that empirical risk. Okay, that's the idea. So how do we do this? Well, we started with just assuming that the function class is just 2 points. You remember this construction, I think, from last time. Suppose I have only two functions that I can choose from. So it's a very simple machine learning problem. I have two candidates, F1 and F2. Which one should I choose? If you call C1 the set of all possible samples which make F1 look bad, that is, the empirical average here is larger than the true risk by epsilon, I mean the deviation is larger than epsilon, and C2 this set, so those are sets of samples. Well, you know by Hustings bound, by definition, the measure of this, the probability of this set, is smaller than delta. This is the, if you're not familiar still with Hustings bound, maybe this is not so clear, but this is exactly the meaning of Hustings bound. I think it's even more clear here than in the previous definition. Here it just basically says that of all possible samples that make the empirical average deviate a lot from the true average by epsilon, if you just take their whole mass, their whole probability, well, this whole mass is smaller than delta, where delta is exponential minus 2n epsilon squared. So we have two sets of samples. Now, if I take 1 point in either, then it means that the supremum of F1, F2 is either, there's one which is either bigger than epsilon or another which is higher than epsilon. And that's enough to say that the sup is bigger than epsilon. So if I just now compute the probability of this joint, this union of two sets, if I just take the simplifying assumption that if I just upper bound it very simply using something called the union bound, probability of C1 union C2 is smaller than probability of C1 plus probability of C2, then I just get this bound here. So the supremum, the probability of all samples such that either one or the other deviates by more than epsilon is smaller than 2 delta. So this is Hustings bound for two functions. Now let's do it for n functions. So my machine learning problem is the following. I have n candidates. I have to choose one using an empirical sample. But I would like to also bound the difference between the true risk and this empirical risk. I'm going to do this again using a uniform bound. So I'm going to say that for every function there is one of those sets. The probability of the union is smaller than the sum of the probabilities. And within that set, at least one of my functions has a deviation from the true risk, which is higher than epsilon. The empirical risk is further away from the true risk than epsilon. So again, I can say that there exists an f in the set of f1 to fn such that pf of f minus pnf of f is bigger than epsilon, is equal to this probability, which is, again, reduced by union bound to n times the probabilities. Okay? So if you just rewrite this inequality, well, you get the Hustings bound for n functions, and you can also rewrite it in the way we've been doing, which is that with probability at least 1 minus delta, you set this to be delta. With probability at least 1 minus delta, the true risk of G is smaller than the empirical risk of G plus this bound here. Okay. So if you've been rereading the slides, sometimes you might notice something. Sometimes we have a soup of the absolute value, and sometimes we only have the soup of the value itself. Okay. So you might think that those are two different elements. Usually when you have the absolute value here, you will have a term 2 that will appear here. It's a natural result of the inequalities that we use to prove Hustings bound. Why sometimes do we only consider the difference without the absolute deviation? Well, because again, the problem is not so much when Pn of f is higher than P of f. The problem is when Pn of f is smaller than P of f. So I told you last time, this situation here, for this point, for this G, for instance, is actually desirable. If you're very lucky if this happens. If this we don't really worry about the fact that the empirical risk might be higher than the true risk. What we worry about is when the opposite happens. And here, for instance, there is a very clear instance, even restricting ourselves to G, of somehow overfitting. Because we're choosing a function Gn which has low empirical risk, but this true risk is quite high. So what we're looking for is a bound which says the true risk is smaller than the empirical risk plus some constant with high probability. So this is what we're trying to obtain. So we discussed last time, but I think I'll just go very quickly, that using these techniques, we can very easily obtain another type of bound, which is a bound on the true risk of Gn with respect to the best possible risk in the function class. So remember that we're also interested in this bound, the bound with respect to the true risk of Gn and the best possible risk in the function class. What is the difference between this and this? We would like this to be not too far from this ideally. So by this we say that we want this to be smaller than the best possible risk plus some term which will depend on n. Okay? So you have to catch the intuition of those bounds, which are just simply that we want to know basically how closer we can get to the best possible quantities depending on the number of points n. Okay? So the smaller this bound is, the smaller those bounds are, the better, always. And what you can see is that those bounds are controlled by basically here n, big N, the number of functions, and small n, the number of points. And they go in opposite directions. If I have a lot of functions, my bound will be looser, so I would have less guarantees. If I have a lot of points, my bounds will be smaller, so we'll have a better guarantee. Okay? If I give you an algorithm which is such that the true risk of my estimate is smaller than R of G star plus a very small quantity, it's an excellent algorithm. It's really a very, very good algorithm. So this is what we're trying to understand. So now we're going to extend this approach, because arguably there's not so many cases in machine learning where you have a finite set of candidate functions to choose from. It's not too common. And if it's a finite set, usually it's a huge set. So even then, it's not. We need something a bit more interesting than that. Typically, if it's a finite set whose size is exponential in some parameters, then you will have here a dependency which will appear in those parameters, and that's not exactly what we want. So let's try to generalize this a bit to countable families. So I have a countable family of functions f, f1 to f infinity. And suppose that we assign a number delta of f to each f, which we use to set, again, a Hustings type of bound. Okay? So this is Hustings bound in the opposite direction. So the probability that there is a deviation which is bigger than this is smaller than delta of f. So for each f, we have a quantity delta of f. Now, if we use the union bound on this, we can also directly say that the probability that there exists at least one f such that this is bigger than this is going to be just simply the sum of the delta of f. So this is, again, just simply the classical union bound that we are applying here. Now, if you set, so for instance, suppose you set delta of f is equal to a multiple of a probability function of f, so the probability functions, then you can say that with probability 1 minus rho, for all f, p of f is smaller than p of f plus this quantity here. So what you have is that we have traded finiteness for a weight here which depends on each function. And then we can have a union bound using those weights, but for each f you will have a slightly different coefficient here which will appear here. So what is the difference between this and this? Well, just think for a second, just think for a minute. Big N is a countable set, right? If you have n functions, it's a countable set, it's a finite set. Imagine that we use a prior weight 1 over n for each function. Then if we do that, then if it's p of f is 1 over n for every function, then we get 1 over n. So we get log of n. We get the previous result. So this new result generalizes the previous result. Okay? So we have found a way to come up with Hustings bound for a countable set of functions if we can define a p of f such that the sum of p of f is equal to 1. So p of f will be very, very small for many functions. For most functions, it will be very, very, very small. So how can you come up with a p of f, for instance? How could you define a p of f? So you could find a way to have a prior on your functions. For instance, if you're thinking about, let's say you have a hyperplane classification, and you only consider functions whose directions are given to you by a rational vector, rational numbers. All of this is countable, and then you can start coming up with a prior on the directions which will sum to 1, for instance. So this can be done, but it's a bit difficult. First, it really requires that you put a lot of knowledge into defining a p of f to get your bound, and that's not trivial. And the other thing is that still it's not exactly what we want, right? If you just think about hyperplane classification, the size of the hyperplane is not exactly a countable set, right? It's just a continuous set. So we start seeing that there is a when you start going into infinite sets of functions, you need to define somehow weights, and that's a bottleneck. So here is when Vapnik and Chervonikis came up with an idea which actually gives a different direction to prove such bounds. And this applies for infinite set of functions, infinite and continuous sets of functions. So here's the idea of Vapnik and Chervonikis. What they argue is that what really matters when you see a function, you see a sample z1 to zn, is not exactly how many functions can operate and how complex the space of functions is in itself. The only thing that matters is the values that the functions take on those points z1 to zn. So keep in mind that each f here is in a loss class. Okay, it's just reminder, it's just the functions which to z equals x, y associates 1 of g of x not equal to y g in the function class g. So of course this can only belong to 0, is either 0 or 1, right? So if you just ignore this for a second, suppose that we have z1, zn. I take one f in the loss class. So somehow you can think of this as taking a g in the set of functions that you are considering. And now you look at this vector, fz1, fz2, fzn. This vector is just a vector of binary numbers. Okay, it's zeros and ones. Now, take the set for all possible functions, all of them. What you get is a set of binary vectors, right, of size n and with elements 0 and 1. So the first thing that you can say is that fz1 blah blah zn is a large, usually it's large, finite set of binary vectors in 0, 1 to the power n. Okay? So what is the maximal size? Well, it's written here. Sorry. I was going to ask. What is the maximal size fz1 zn can have? It's 2 to the power n, right? If I have n binary numbers, I can have 2 to the power n combinations of them. Okay? Now, imagine my function class is very simple. It's just one point. Sorry, it's just one function. What is going to be the size of this set? If I only have one function, what is the size of this? Okay, I just call it F1. Anyone? Okay, maybe let's do this. Okay, answer 1 is 0, answer 2 is 1, answer 3 is 2, answer 4 is 2 to the power n. Okay, I'll just give you, let's say, so f is equal to f1. What is the size of this set? Okay, it was a simple question, but I just wanted to check. So 2, 4, 6, 8, 10, 12, 13. And we have 8 answers, so I will assume that the 5 who have not answered were not very clear about this. So the correct answer is 2. Yes, it's 2. Basically, I'm just saying this. If f, this big F is just one function, this is just one vector. So this big set here is just 1. The size of this big set is just one vector. Okay? Now, if I start adding, if I have two functions, can you give me for sure what is the size of the set? If I have two functions, what would be the size of f? What can it be? That's it. 0, 1, 2, 4, I don't know. I have trouble getting it back. I think I'm doing something wrong here. again, now f is f1, f2. What is the size of this? It's two functions now. The countdown is going on, yeah, okay. It's not a very difficult question, but you have to think about it for a second. Okay, you got it wrong. We don't know, because it might be 1 or 2. If the function here, well, in the trivial case that f1 and f2 are the same thing, then of course, then this f is still going to be 1. Okay? So the upper bound, if we have n functions, okay, the upper bound on this is big N. But that's assuming that each function will produce a different classification result. Okay? So this is the slightly different. So basically this quantity does not increase as fast as the number of functions. Okay? This quantity is basically, I just should write it here. The size of this set is the number of possible ways in which the data z1, zn can be classified using functions in F. Okay? There are different ways you can do that. And if you just take all possible different classifications, then you will get this size, this number of vectors. So the more complex F, I think you will agree, the larger this set will be. And actually, if you can come up with a way to classify this in as many different ways you want. So how many different ways are there? 2 to the power n. For each observation, it's either the yi that you got that was given to you or the other way around. Okay? It's either this sign that was given to you, yi, or minus yi. So for each different point, you have two choices. And if you have a function class which is rich enough, you will be able to do whatever you want. And then you will get that this set is exactly of size 2 to the power n. Okay? Now, this here applies for one particular sample, z1 to zn, okay, which is here, given here as an index. Now, imagine that I define the following function. The supremum over all possible points in all possible samples of size n of the size of that set. So that supremum is called the growth function. So again, what is an upper bound on SF of n? An upper bound on SF of n is 2 to the power n. Okay? SF of n is always finite. Because if I look for the set for which I can split the data in the most possible different ways, I will never obtain more than 2 to the power n different ways of splitting the data. Okay? So this quantity is called the growth function. So here is Vapnik's and Czerwonicki's first theorem. For any delta positive with probability at least 1 minus delta, so this is the second formulation of Hustings inequalities, the true risk of G is smaller than the empirical risk of G plus 2 times this function here. And what do you recognize here? Well, if you look at what we had before, we had this kind of formula here with a bound on square root and the log of 1 over p of f, or square root and a log of n here. Okay? Sorry, so it's this one that I want to show. Log of n plus log of 1 over delta. So what is different here? Well, it seems that we have added two things. Those two here, the terms 2 and 2 here came up at some point. There's 1/2 here which has gone here. Instead of having log of 1 divided by delta of f, we have log of the growth function of 2n not exactly n. Here we find a growth function of n. Here we have the growth function of 2n. And log 2 over delta. This is the same as that we had before. So we will prove this result. And to prove it, we will need two lemmas. So one is called the symmetrization, and we'll explain it. And the second lemma is called Chebyshev's inequality, and I will take it. I will assume that we have it. So let me just go into the proof. So the first thing I'm going to prove is the symmetrization lemma. So let's look at the lemma itself. So for any t such that nt squared bigger than 2, that's just a technical assumption. And here is why it's called symmetrization. We are going to consider that we know n prime more independent samples of p. And actually, the notation is not very clear here. It's another n samples of the same distribution. The number is n, but we write prime to say that it's different samples. Okay? In that case, we can prove that the probability of the supremum, so this is the classic Hustings bound type of quantity, the supremum of the deviation. And now it's going to be smaller than 2 times p, the supremum over the empirical average over n prime. So this is called a ghost sample. It's a second sample that we consider, minus Pnf of f. So what we're doing is the following. Suppose that I have the true P of f somewhere. I have one sample of size n. The difference between P of f and Pn of f, the probability that this is bigger than some t. Now I'm going to consider another sample somewhere. So I should probably draw this at some point. I'm going to play with 3 different quantities. One which is in blue P of f, one which is Pn of f. So remember that this is the gap that we try to control. And the probability that this is bigger than epsilon, well, we can play with the fact that, I don't know if I should use a different color. Okay, I'm going to use another sample, which I'm calling the ghost sample. And I'm going to say that the probability that this here is bigger than t. This probability is even, the supremum over all possible f of this is bigger than t, is itself controlled, bounded, by twice the probability of the supremum between those two differences here is bigger than t divided by 2. So let me just prove this. So I'm going to consider for one n the supremum of p minus Pn of f is going to be, I'm going to write it Pn of, let's say, Fn. Okay, so for one n, sample size n, I can compute the function for which the gap between the true risk and the empirical risk is maximal. This is basically like doing this. It's like starting from here and here and scanning within those elements for which point basically the difference between the blue curve and the red curve is maximal. So I call this Fn. So now what we have is that in terms of events, the probability that, the event that P minus Pn of f n is bigger than t times p minus pn prime of fn is smaller than t divided by 2 is equal to, this is just the product of the two things, so it's just Pn of Fn bigger than t, and this is the n sign, p minus Pn prime of Fn. Sorry, I'm going to put it the other way around. So if you think about this, if this happens, then I'm just going to write it here on the side. I have that Pn of Fn is smaller than P of Fn. I'm sorry, I'm a lefty, so I should do it this way. Yeah. Minus T. And I also have that P, so this is the second one, P of Fn, which direction, minus T divided by 2 is smaller than Pn prime Fn. Okay? So what I'm going to do now is I'm going to take 2 minus 1 to get that. In that case, if I have this and this, then necessarily Pn prime of Fn minus Pn of Fn is bigger than T divided by 2. Okay? Basically here I get that if I just do actually 2 plus 1 and I write this plus T minus like this, I just take this plus this, those two terms cancel out, T minus T divided by 2, and I get this. Okay? So in that case, I have that if this and this is true, then this is necessarily true. So basically this is smaller than just the condition that I have this, which includes more cases than this and this. So I have that Pn prime minus Pn of Fn is bigger than T divided by 2. Okay? So now what we're going to use is the second lemma which is given here, which is Chebyshev's inequality. If I just take if I just now take the expectation with respect to the second sample, so let me just erase this part. So now let's take, so this here, we have just proved this inequality by introducing this second ghost sample. And Fn here is again with respect to the first sample. Okay? So now we're going to take the probability with respect to the second sample. Okay? So if we just take the expectation of this with respect to the second sample, then we get this doesn't change. It's just 1p minus Pn of Fn bigger than T times this becomes the probability with respect to the second sample of P minus Pn prime Fn smaller than T divided by 2, itself smaller than the probability with respect again to a second sample of Pn prime minus Pn of Fn bigger than T divided by 2. Okay? So now if you just directly consider Chebyshev's inequality on the first term here, you're basically taking an average with respect to, you're averaging the gap between this and this here. I'm sorry, I'm not sure. Yeah, I'm not sure I gave you the good version of, this is the Chebyshev's inequality with absolute values, but the one without absolute values is slightly different. I will update this in my slide. Sorry. Then what you can show is that this is itself smaller than 4 times the variance of Fn divided by nt squared. And remember that Fn can only take values between 0 and 1. So the variance of Fn is necessarily smaller than 1/4. And so we get that this is smaller than 1 divided by nt squared. Okay? So basically the result that we get is that this times, oh sorry, I went a bit far. I went a bit too fast. I wanted to show you this. So I would write it here. What we get here is that the probability of P minus Pn prime of Fn is bigger than T divided by 2 is smaller than 1 divided by nt squared. Okay? So basically, the probability with respect to P prime of P minus Pn prime of Fn smaller, bigger than T2 here, but here smaller than T2 here is bigger than 1 minus 1 divided by nt squared. And this is a term here that we had there. So we can again lower bound this by 1 minus 1 nt squared. And now if you take just simply the probabilities with respect to the first sample, then you will get that the probability that the soup, remember that Fn was the soup, so we can replace it, P minus Pn of F is bigger than T. Is going to be smaller than 1 divided by 1 minus 1 divided by nt squared times the probability here of the soup of Pn prime minus Pn of F bigger than T divided by 2. Okay? So what we have proved is this result here. So this technique of using a ghost sample, another sample, is just a way of bounding the difference between the true mean and the empirical mean by something which is the difference between two empirical means. So it's a very powerful technique if you think about it. And why is it useful in this case? Well, because now that we use this, we can use it to compute, to basically get all the pieces together to get the result here above. So how do we do this? Well, we will just say that, so I can erase this. This is just the symmetrization lemma. So what we can now use is just simply, well, here I'm assuming that you can reuse Hustings bound in a slightly different way, which is the probability with respect to the first sample, the deviation with respect to the second sample, the fact that this is bigger than t is smaller than exponential minus nt squared divided by 2. So this is a slightly different version of Hustings bound. So now if you just compute, if you just write the probability of the supremum, so we assume that this, we'll assume this is a slight generalization of a different version of Hustings bound. If you just write the sup of p minus pn of f bigger than t is itself now smaller than 2 times the sup of pn prime f minus pn of f bigger than t divided by 2. So this is the symmetrization lemma. So of course, actually, if you really look at this quantity, this just depends on this first sample n and the second sample n prime, right? So it's just 2p times the supremum over all possible functions in the function class, all possible vectors. Sorry, in the set of different classifications of z1 zn z1 prime zn prime of pn prime minus p n f bigger than t divided by 2. So here we are going to use again a union bound. This is a finite set. The size of this set, you remember, is just the size of a set like this is what we call the bars of fzn, and the supremum of this basically is the growth function. So what you get is that this is itself smaller than the growth function of f of 2n. So we're taking with respect to 2 samples of size n of the deviation of p n prime minus p n of f small bigger than t divided by 2. And this, now you can use this version of Hustings bound to basically write, I'm sorry, I think I forgot. Oh, yes. So here we have a t divided by 2 here. So the term here is going to be exponential minus nt squared divided by 8. And the fact that I have a half, no. Yeah, I get this. This is not exactly what I'm getting here. And now if you just use the inversion using as we were doing as usual, you will get the result that we wanted. So I'm not sure it was the best idea to do this on the blackboard here now, but I just wanted to give you an idea of how you can get such results. there is a reason why there is a 2n here which appears, is that because to prove this, we have gone through the definition of another sample, a ghost sample, and then we've started playing with that ghost sample to bound the deviation between the true and the empirical risk by the deviation between two different empirical risks. And then what is really interesting is that the difference between two empirical risks here can be computed through the growth function of a size 2n here. This is the key argument here. So using this plus the fact that we can now introduce the growth function of 2n and using a union bound in the end, plus, so Chebyshev's equality, sorry, was used to prove this. But using this lemma here, we can include a bound here which depends only on the growth function with 2n sets. So this is rather technical, and actually, if you remember, I said that one of the problems of this approach here was that it's not necessarily easy to come up with a P of f, a good prior P of f. But if you can compute this function, then you can come up with a bound which is uniform, which works for the whole function class. But the problem is actually how do you compute this growth function here? This growth function is actually very difficult to compute. It's the supremum over all possible observations of the number of ways you can classify data using the function class that you're considering. So it's fairly difficult quantity to compute. So what Vapnik and Chervonikis came up with then is a different criterion. And the biggest contribution of their new approach is to consider something, a quantity called the Vapnik-Chervonikis entropy. So if you look at this, all those bounds here, if you look, for instance, at this quantity here, it doesn't depend at all on the true probability of the data. Remember that a cornerstone of the construction that I've given so far is that there is a probability regulating the operations of pairs z's, x and y. Here I'm taking a uniform supremum over all possible observations. What Vapnik and Chervonikis propose is, rather than considering the supremum of this quantity over all possible points, they consider what they call the VC entropy of the function class with respect to the data distribution. Okay? So again, the VC bound, this bound here, will hold whatever the distribution of the data. If you want to find something that's a bit more narrow, but more interesting, since actually the data that you're seeing is not given to you completely randomly, the data that is given to you and the areas of the data that you care for are the ones that are with high probability with respect to the model. Sorry, not the model, the true distribution. They propose this quantity. So HF of n is the log of the expectation of the size of those sets. And in that case, what they propose is another bound, which is for any delta positive delta with probability at least 1 minus delta, then the risk of G is going to be smaller than the risk of empirical risk of G plus this bound here. So I think you can see why this is more important. This approach is more important than the previous one. Here we have a quantity which depends explicitly on the probability distribution of the data. Here we have an empirical distribution which also depends explicitly on the distribution of the data. So somehow this bound really is much improved if you take into account the distribution of the data too. And taking into account the distribution of the data, you can use this Vapnik-Chervonikis entropy. So I will not prove this result now, But this is still very difficult to prove. Sorry, not difficult to prove. It's still very difficult to compute. Okay? So there is one downside of this bound which has been solved. So one downside of this bound is that it's uniform for all distributions of the data. And actually what we care of is just the true risk with respect to one distribution. But there's still another downside, which is that we still cannot compute neither this nor this. So this is I think probably the biggest contribution, which is to introduce the VC dimension of a class of functions G. So this is probably the most important definition in this later part of the course. So the VC dimension, the Vapnik-Chervonenkis dimension of a class of functions G is the largest n such that Sg of n is equal to 2 to the power n. So since n points can have 2 to the power n configurations, the VC dimension is the largest number of points which can be shattered, like split arbitrarily with respect to any labeling by the function class. And here I'm writing that the VC dimension of linear classifiers in RD is exactly d plus 1. So let me just illustrate this. I have a few. I will just proceed by examples. Imagine that I am in R2. Okay? N equals 1. If I have 1 point in R2, let's say this one, then it's very easy to set this point. So I'm going to write, for instance, my hyperplane like this. And I'm going to define the direction of the normal vector. Here I'm going to say that this is plus 1, and here it's minus 1. So you can see that this vector here can be assigned a red value, but it can also very easily be assigned a blue value, if I just flip the direction of the normal vector, right? So if I just consider the set of all hyperplanes in R2, then for any point, you can very easily see that I can label it as a plus 1 or a minus 1, right? So in this case, the size of f Z1 is equal to 2. Okay? Let's consider the case n equals 2. 2 points. So I'm going to write the original points here. Let's take 2 points. And I'm going to consider all possible cases, all possible labels. I wanted this one to be red and this one to be blue. I want this one to be red and this one to be red. I want this one to be blue and this one to be blue, and I want this one to be blue and this one to be red. Is it possible to find a hyperplane which will do this labeling? Well, it's indeed very easy to find one. I just take this hyperplane with this direction. So positive part is red and negative part is blue. I can do this. I can do this. And I can do this. Okay? So this, of course, is the red part. This is the red part. This is the red part. This is the red part. And blue part. Okay? So for 2 points, the number of labelings that I can come up with for those 2 points is, suppose this is the number 1, this is x1 and this is x2, z1, sorry. z1 and z2. Okay? Suppose this is z1 and z2. Then here I just said z1 was 1, z2 was 0. z1, z2 were both zeros. Here it's 0, 1, and 1, 0. Sorry, no, 0, 1, and 1, 1. Okay? So how many possible combinations do I have? I have 4. How many did I cover? 4. So in this case, the size of the set, if you want S2 of the set of hyperplanes, is still equal to 4, and it's equal to 2 to the power 2. Now consider the case where n equals 3. Okay? I will have 3 points. So I'm not going to do all the examples, but let's say it's x1, x2, x3. So again, do you think that I can do all possible different combinations of labels? Could I come up with a hyperplane which will be 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, and 1, 1, 0, and 1, 1, 1? Well, yes, it's easy to see that if I just pick one of those randomly, I will, not randomly, I just pick one of those, I'll be able to realize it. So let's consider this one. This one says that x1 and x2 must be red, and that x3 must be blue. Well, it's very easy to define this hyperplane, which will split them here like that. Okay? So we don't need to go through all those examples, but it's easy that you can do all of them. Now, if n equals 4, this is where we have a problem. Because if n equals 4, can I use hyperplanes to obtain this labeling? Of course, there's no way I can define a hyperplane that will give me those labels like this. If I just define it, if those two here need to be red, it means that they have to be on the same side of the hyperplane. And well, basically, I don't know if you remember, I briefly mentioned that two sets are linearly separable if their convex hulls do not intersect. So here you can very easily prove that the convex hull of this 2 points is this segment. The convex hull of these 2 points here is this segment, and their convex hull intersects, so they are not linearly separable. But intuitively, visually, you can very easily see that there's no way you can find a hyperplane that will not enforce that those 3 points here will be red, or those 3 points there will be red. So in this case, for RD and D here equals 2, I've just illustrated that as long as you have 1 point, 2 points, or 3 points, you can come up with any arbitrary labeling that you want. When you reach 4 points, you cannot. There are some labelings that are not accessible to your function class. And so this is the VC dimension. The VC dimension of linear hyperplanes in the plane, in R2 equals 2, is exactly 3. So it's very important to see this as a quantification of how complex the function class is. For instance, if I didn't restrict myself to linear hyperplanes, but I was restricting myself to quadratic functions. So instead of being just whether a function is a linear function is positive or negative to split, I would just consider quadratic functions. Well, imagine the quadratic function which is somehow centered here is equal to 0 here. And the function would be something like x minus x0 transpose some matrix here. Now we get some kind of ellipsoid if you want. Like this. And I will make sure by adding some constant here that this here is equal to 0. That this here is positive and below it becomes negative. So in that case, if I use quadratic functions, I can very easily split 4 points in any way I want. It's easy to see. The problem is if I limit myself to just hyperplanes. So here we have a quantification that hyperplanes are less powerful than, let's say, quadratic functions to label points in RD. And the quantification that Vapnik and Chervonenkis propose is this one. It's n, the VC dimension is the largest integer, n, such that Sg of n is equal to 2 power n. Okay? So the VC dimension of a function class is always going to be an integer. So what Vapnik and Chervonenkis now prove is that given the VC dimension h of a family G, we can prove, so it takes a bit longer, that the risk of G minus is smaller than the risk of n of G plus this quantity here. And this, here you can have access at last to a bound which is a bit more tractable, because you can see that h, at least in this case, we have been able to compute it. For linear classifiers, at least, we have been able to compute the VC dimension. And now we have a bound on the true risk with respect to empirical risk and this VC dimension. So the way you prove this is actually using a lemma proposed by the following people separately, I think. If you have a class of functions with finite dimension h, then the growth function, remember which the growth function here was appearing here, then you can upper bound the growth function by this quantity here for any n, and in particular for large n, which is actually what we're really interested in. For n which is larger than the VC entropy of a function, we have this bound here. Okay? So if you just substitute to this bound CG SG of 2n here, this bound here, so you put 2n here, and you just put it in the log here, well, you get exactly the bound that we had before, except that now it depends explicitly on the VC dimension. Okay? So combining this result with the previous VC Vapnik-Chervonenkis theorem, which we had here, we are able to explicitly write how we can control the true risk of a function g with respect to the empirical risk uniformly. And this term here depends on h times log of n divided by n. Basically, this is the dominant term in this bound here will be this quantity here. So, what can you exactly say about? I mean, what can you intuitively say about this bound? Well, the higher the VC dimension will be, the more loose this bound will be. The bigger h will be, the less you can say that the risk, empirical risk of a function g for all g's here is not too far from the true risk g. So this bound here suggests an approach where you choose a function class g of low VC dimension. Okay? So if you want, this was the main reason why Vapnik-Chervonikis was started advocating SVMs, support vector machines. Basically, he came up with a result which shows that when you use hyperplanes, so we all know that hyperplanes are robust and more robust than polynomials or higher order polynomials, etc. But this was a way to quantify exactly this. If you choose functions which have low VC entropy and of them hyperplanes, then you get a bound which doesn't go, the numerator here doesn't increase too fast with the number of points n, whereas the denominator here in the square root of n will decrease relatively fast to give you a nice bound here, a nice difference here. So are there any questions? Let me just check. Okay, no, actually we don't really have time. So you can say that one of the goals of statistical learning theory is to come up with this kind of bounds. Sometimes they're not so useful in practice, but at least they give you a good guide, if you want, on why sometimes you should limit yourself to function classes, simple function classes, and not use very complicated architectures. So theory in this case is really a guide. It's really a, who said this? So theory is the first term in the Taylor series of practice. So if you just start using practice, practice is the sum of many things, and the first order term, fundamental term, should be theory to help you guide. And then you start adding other refinements such as optimization algorithms, data structures that help you manage the data fast, etc. But you should be guided by those principles. And I think that this term here is probably the most important of those 2 or 3 lectures. The gap between the empirical risk and the true risk is, if you are using a function class of VC entropy H, is controlled by this. So rather than start with the 5 minutes that we have left, I will just close the lecture now. No questions? Just want to, we have 4 or 5 minutes, so. No questions on the assignment either? Well, now it's a bit too late, but you can still ask questions if you want. Okay, so I will put online an assignment, the last assignment, probably today or tomorrow. You will have, again, 2 weeks to complete it. Next week will be the last lecture. So I will see you again for the last time next week. Thank you.